Afternoon. It's going to be hard to talk after those two inspirational talks. There's no way I'm going to match that, so keep your expectations low. My name is Mark Kramer. I'm going to talk about the clinical information modeling and profiling language, CIMPL, CIMPL. And just as a brief introduction, I serve as the chief engineer of MITRE's Health Technical Center, which is located in Bedford, Massachusetts. And MITRE, for those of you who haven't gotten sick of us already, with all the folks here, is a nonprofit, federally funded research and development center with quite a broad range of interests, and healthcare is a large and growing segment of that business. And we've been doing healthcare at MITRE for about 10 years, and it's grown to have about 600 people involved. And some of the products that we have, or products or projects that we've worked on, are given by all these wonderful logos. In the talk, the keynote by Greg Simon, you heard him mention M-Code. That's the Minimal Common Oncology Data Elements project, which I'll be talking about tomorrow, so that's one of them. And you heard Steve Posnack of ONC talk about Inferno as a testing tool. That's another one. So there's some interesting stuff going on. Many of you may have also encountered Cynthia. It's a simulated data generator, and it's been used for testing a lot of FHIR applications. So there's some good things going on at MITRE. Now, I'm going to talk about profiling, and during this conference you may have heard or already know about two profiling methods, tools. One is Forge and the other one is Trifolia on FHIR. They're both excellent tools. I've used them both. But I'm going to talk about a third way, and one you probably haven't heard of, which is CIMPL, the Clinical Information Modeling and Profiling Language. And what it is a high-level language for creating profiles. It's all open source and it's free. And I highlighted language for a specific reason. It's different than the normal, or at least the other ways to create profiles. I'd characterize the typical way to create profiles as using a profile editor. You've got some user interface that's really just editing a structure definition, which is your profile, and then there's a tool to produce a implementation guide and the profiles with a little bit of configuration effort. So really what you're doing is you're taking this massive structure definition, which is this horrendous large JSON object, and you're configuring it using a visual interface. So CIMPL is really quite different. What it is a object-oriented declarative language where you describe what you want in your profiles, and you execute this language and you produce a number of different artifacts. The artifacts include an implementation guide, the profiles, the extensions and value sets, etc. Also data dictionaries, graphical views, class browsers, and I'll explain momentarily about the class structure and why that's important. So the focus is really on modeling. You're using this language to describe what you want. It's not on the ins and outs of a structured definition. And that's a really different point of view. So why a language? Why on earth? Well, the grammar in CIMPL is optimized to do exactly what you need to do when you build a clinical information model. And it includes all the things you need to do in FHIR when you profile. And I'll go through that. But you notice that in the world of computers that all complex projects use languages. There have been a few attempts at graphical visual editors, but if you're doing a complex project, you're writing code. And a lot of us are quite comfortable writing code, and we know how to manipulate and control and that sort of thing with code. So here you're writing a little bit of code to get a lot of bang for your buck, okay? And we believe that it's 10 times faster than editing structure definitions one at a time. And I'll explain about the agility point of that. So we believe it's much more powerful than other techniques for creating profiles. And, you know, you might ask, why is that important? Because ideally, you know, you go through a profiling project in kind of a linear fashion, ideally. You define the use case, you talk to clinical experts, you start collecting the requirements, you translate those requirements into an information model. At that point, informaticists get involved to define value sets. Then you map those to FHIR resources, you produce the FHIR artifacts, you start implementing, and you deploy, and you're done. Well, ideally, maybe. And if you do it this way, and you're you know, much smarter than I am, and you get through once, then indeed, you know, maybe a profile editor is good enough. But I've done big projects, and what I find is that in reality, there's a lot of redoing, modifying, refactoring, renaming, rejiggering, redoing. At the same time, you're building out more and more. You're taking into account more and more people's opinions as the community grows. And so you are not following this linear path. You are doing a lot of revision and refactoring. And so CIMPL has a lot of reasons that it's very agile in this type of situation. For one, it's a language, and we know that we can, you know, quickly do things like global search and replace, which I promise you is going to be your best friend forever. When you do a project like this that's large and complicated, you're going to be revising over and over again, trying out new ideas, going back to the clinicians and saying, is this right? But CIMPL also allows you to write once and use many times. The reuse in CIMPL is absolutely maximized. So if you define something, the example I am anticipating is body location. So if you build a little model of body location, actually in FHIR, that's very, very inconsistent. Sometimes body location is just a code. Sometimes it's an object, and that there doesn't seem to be any pattern for why one, why the other. So in CIMPL, you define one pattern that you want to use over and over again, and then you can reuse it. A big thing is source code control, and most of you will be familiar with things like GitHub. So you know that you can do distributed collaborative development by branching, everyone working on different bits and pieces of the project, then merging them together. And to do that successfully, you have to have a meaningful diff. You can often diff files, but if one little change that you make changes around the whole file, you're not going to have a meaningful diff. Well, in CIMPL, you get a meaningful diff. And the other thing that is agile about CIMPL is that you can handle all the versions, all the major versions of FHIR all at once. So you develop one simple model, and you can export that to DSTU2, STU3, and R4. So before I start explaining, going deeper into those, I'm going to talk about, I'm just going to give you an example of what CIMPL looks like. So this is an example which is pretty easy to follow. It's just the dimensions of a tumor, okay? So it's got length, width, and depth, right? And they're related to each other. There's also this other thing called size of the gross tumor bed. When they excise a tumor, do a biopsy or a surgery, that's the size around the tumor. So I'm going to walk you through that, and this is the description of this relatively complex thing. So the first two, I wanted to mention at this point that you can edit these files in any text editor, okay? Any text editor you want, whatever your favorite one is. We have a nice plugin for Visual Studio Code, so that one is attractive. And by the way, this description gives rise to almost 3,000 lines in a structure definition. So it's pretty compact compared to structure definitions. So let me walk you through line by line. So the first two lines, you're defining this new thing, tumor dimensions. Its parent is going to be a coded laboratory observation. And the mere fact it has a parent is kind of interesting because it tells you that CIMPL is an object-oriented framework. So you could inherit from classes and build on these classes. In this case, there's a built-in class that comes with CIMPL called Coded Laboratory Observation, which is like an observation, but it has certain constraints that tell you that the result is going to be coded. Then we have a description, which is pretty self-evident, and then a property, related tumor. So there's an object that represents a tumor in this model, and this is the tumor. This is the measurement that relates to that tumor. So we have to have that, otherwise that doesn't make sense. So it's a new property that will become an extension automatically. CIMPL will produce that without you worrying about what's an extension and what's not. Then there's a bunch of statements that are constraints. So going through those one by one, we're fixing the code here of this observation to be a SNOMED code for tumor size. It's not going to have a data value. It's actually going to be a set of components. So you'll see that the data value and the panel members, which are the related observations, are zeroed out. And we're going to require these components. And the components that we're requiring now are the longest dimension, the secondary dimension, and the tertiary dimension, as well as the size of the gross tumor bed. And what we're doing here is slicing. So the word includes is the only thing you need to know to do slicing within CIMPL. So it is, in fact, simple compared to raw slicing of FHIR objects. So that's kind of the idea of what CIMPL looks like, gives you that idea. The other thing you do is you define value sets. You can do value set binding. And there's two ways you can do it. You can have explicit value sets or implicit value sets, and you can mix these flavors together. The explicit flavor just lists codes. Here we're taking LOINC answer codes. And then the implicit style, which is echoed in FHIR, says take all the codes descending from a certain node in a hierarchical scheme. In this case, it's SNOMED. So there's a simple grammar for that as well. So since you've got this description of what you want to build, you can now go to GitHub and you can branch and work on your own branch and then go back and compare different versions, right? So now you can distribute the development around and you can see the changes line by line in a meaningful way. You can review the changes, you can accept them, you can do pull requests and all that. And you heard Greg Simon in the talk earlier talk about M code. Well, my team developed M code, and we did it over a period of several months. And this is a visualization of part of that development where we used a lot of branches in GitHub doing CIMPL, where we had a lot of branches and merges and so forth. And this is just a bit of this. So we had 3 or 4 different people working on multiple branches to create this, to create M code. M code is, I'll talk about it tomorrow. It's got about 20 to 30 profiles, and it's a fairly complicated thing for a minimal set of oncology elements. But the other thing about that was that we were working with 20 oncologists, surgeons, pathologists, and they all had opinions. So that round and round thing I showed was very much in evidence, and that's how it was reflected. So that's a little bit about CIMPL, but there's some advanced features as well. So I mentioned that CIMPL is object-oriented. You create your model classes by extending, subclassing other classes that exist. So you can create your own, or you can use things in a library that we provide to subclass off of. The base library we call Objective FHIR because it is an object-oriented view of FHIR. It has, it's a topic unto itself. Basically, it takes FHIR, which is very flat. There's just like resource, and then there's 150 resources. So it arranges them in a class hierarchy that was thought out over a long period of time with common properties. And this class hierarchy goes on beyond the resources that were that are provided in FHIR. And you saw one before, the laboratory observation. So that's a subclass of observation. And it's based on US core. So you can map to the US core laboratory observation. And it's an abstraction. So it actually is an abstraction that cuts across the versions of FHIR. I mentioned that earlier, that you're sort of doing this meta model which is not stuck on one version of FHIR. It actually can map to all the versions of FHIR that exist. And because of that, the output, when we generate an output, it's more interoperable. If you're going to do a version 2, if there's a version 2 server, it's going to have the same semantic concept as a version 3 server or a version 4 server. So the same model is expressed in those different versions automatically. And I gave the example of body location before. I'll dive into that just a little bit. So basically everything you build in CIMPL is reusable. So if you build a description of body location, and here we've described body location with a code, a laterality, orientation, and relation to landmark, or multiple relation to landmarks. This segment can be reused anywhere, anywhere you have a body location. And it can also be subclass. So we were doing breast cancer, and we defined a breast site, which there's a particular way that you measure, that you describe the location of a tumor in breast cancer, which uses clock direction and a landmark from the nipple measuring out. So we specialized the body location class by subclassing, constraining, and extending that body location. So then that's available to everyone who is using CIMPL as a reusable component. So the other thing that I mentioned a couple of times is this ability to cut across versions. I guess I preempted myself a bit, but since everyone is on a different version of FHIR, Argonaut and Cerner and Epic are still in, and a lot of providers are using these tools which are still on DSTU2. It pays off to have something where your migration path is going to be paved for you. So we do that by basically using CIMPL as this meta language, and then you can execute this one source code and produce the implementation guides and profiles and extensions in multiple versions of FHIR. So that's an advantage going forward. Our objective FHIR is based on R4, so it's up to date, but we can back map to DSTU2 and STU3. The other thing, we have lots of outputs from CIMPL. We can transform that source code into lots of things, and one thing that we do is a class library. This library, you can look at it as a class hierarchy, and this may look familiar to some of you who've used JavaDoc. So this is kind of a JavaDoc version, and you can see how tumor has been derived from body structure, derived from condition, from situation statement, then clinical statement, then you recognize domain resource. So some of those classes in the middle are part of the abstraction layer of objective FHIR. And we have lots of documentation now. We just had a major release, CIMPL 6.0. The whole project is about 3 years old, so it's quite mature. And we have tutorials, installation guides. It's all open source. I mentioned that before. And it's free to use. We have an extensive authoring guide and reference manual, and also an IG for the objective FHIR class library. So throughout the slides, which I guess are available, you'll see these various links. You're welcome to visit them and download. And as I said, we're, it's a mature framework now. Tomorrow, I'll be talking about MCode. MCode is a project that used CIMPL as a development language to develop this cancer-oriented IG. It's actually one of 4 or 5 or 6 IGs that we've done at this point using this same framework. So we did one for occupational data for health. We did one for skin and wound. Several of those have been balloted through the HL7 process. So that's it. Any questions? I have 3 minutes.